Next example of linear dependent and independent types show that e raised to x, cos x, sin x are linearly independent in function space. That let k1. So we have to determine these three vectors are linearly independent. We have to show these three vectors are linearly independent. So there are three vectors. So take three scalars. Let k1, k2, k3 be scalars such that k1 e raised to x plus k2 cos x plus k3 sin x is equal to 0. The 0 means the 0 function. Then put x is equal to 0, x is equal to pi by 2 and x is equal to pi we get. So this is somewhat different example of the remaining linearly dependent independent examples. This is some different example. We have to obtain the three equations. In order to obtain the three equations, we have to put x is equal to 0, pi by 2 and pi. We get this. E raised to 0 is 1, cos 0 is 1, and sin 0 is 0. So we have k1 plus k2 is equal to 0, equation number 1. Then substitute x is equal to pi by 2. So k1 e raised to pi by 2. Cos pi by 2 is 0. So sin pi by 2 is 1. So plus k3 is equal to 0. And e raised to pi, k1 e raised to pi. And cos pi is minus 1. So minus k2. And sin pi is 0. So we have is equal to 0. So these are the equation number 1, 2, 3. And we have to solve these three equations and we have to determine the values of k1, k2, k3. Either I use the Gauss elimination method or by using trial and error. That is by adding and subtracting we have this. So from equation 1 we have k1 is minus k2, put in the equation number 3, or we add the equation number 1 and 3. Just add equation 1 and 3. We have k1 plus k1 e raised to pi is equal to 0. So or we take k1 as minus k2 in this equation. We have this minus k2 e raised to pi minus k2 is equal to 0. So k2, take k2 as common, minus k2 as common, e raised to pi plus 1 is equal to 0. And so we have minus k1, k2 is equal to 0 because e raised to pi plus 1 is not equal to 0 quantity. So the multiplication of these two is 0 means one of them is 0, and so k2 is 0. We know that a into b is 0, then either a is 0 or b is 0. One of them is 0. So here e raised to pi plus 1 is not equal to 0 for all value of pi. For all e raised to pi is not equal to 0. E raised to pi plus 1 is not equal to 0. So this e raised to pi is always not equal to 0 quantity. So we have it is minus k2 is 0 means k2 is 0. And substitute k2 as 0, we have k1 is 0 from equation number 1. And if we substitute k1 as 0 in equation number 2, we have k3 is 0. So all these k1, k2, k3 are 0, and therefore the given three vectors are linearly independent. So this is the some different problem on the linear dependent and independent. That is why I have to find the three equations by substituting x is equal to 0, pi by 2 and pi. So the given three vectors are linearly independent because we have the values of all scalars are equal to 0. Next example, determine whether the set of vectors p1 is equal to 5, p2 is minus 6 plus 4x square, 6x plus x square, p3 is 3 minus x bracket square, are linearly independent in p2. What is this p2? p2 is the vector space of all polynomials of degree less than or equal to n with real entries in x. So these p1, p2, p3 are the elements of this obviously p2, because all these p1, p2, p3 are what? Are polynomials of degree either is equal to 1, is equal to 2 or less than or equal to 2. So this polynomial p1 is a polynomial of degree 0. This p2 is the polynomial of degree 2. This p3 is the polynomial of degree 2. After simplification of these 3 minus x bracket square, we have this. So all these p1, p2, p3 are what? Are polynomials of degree less than or equal to 2. So these p1, p2, p3 are the elements of p2, and we have to determine whether these three vectors p1, p2, p3 are linearly dependent or linearly independent. So there are three vectors. So take three scalars. Let k1, k2, k3 be scalars such that k1 p1 plus k2 p2 plus k3 p3 is equal to 0. So after all these examples of linearly dependent and independent, what is your observation? That is, these vectors either we are in p2, that is set of polynomials, or in the function, or in the r3 or r4 or m2 by 2r, whatever may be the vector space, if you have to determine the elements of that vector space are linearly dependent or independent, what we have to do, that just take the scalars. How many we have to take the scalars? If you are given the three vectors, then take k1, k2, k3 as the three scalars. Or if there are if you are given the four vectors, uh, then we take the four scalars and take their linear combination equal to 0, that is k1 v1 plus k2 v2 plus k3 v3 plus k4 v4 is equal to 0. Or if there are three vectors, then k1 v1 plus k2 v2 plus k3 v3 is equal to 0, and find the values of k1, k2, k3, k4. That is the values of that scalars. If values of all the scalars are equal to 0, then the given vectors are linearly independent. And if the values of k1, k2, k3, k4, that is all the scalars are not equal to 0, then the given vectors are linearly dependent. So the procedure for all vector spaces, for all problems of linearly dependent and independent, are same. That is either the vector space is a vector space of polynomials, or vector space of matrices, or vector space of functions. Here if you observe this example, these are the examples of R3, R4, or the vector space may be the set of matrix m2 by 2r. So the vectors are vector space may be m2 by 2r, or r3, or r4, or p2, that is the set of all polynomials of degree 2 or less than or equal to 2. So these are the elements of m2 by 2r. So procedure for all examples is same. So if you are given three vectors, take three scalars. If you are given four vectors, take four scalars and find the values of that scalars. Okay. If all are equal to 0, then set is linearly independent. And if one of them is not equal to 0, then set is linearly dependent. So here the same procedure. Here the three elements of this capital P2 are given. What are that? P1, P2, P3. And then take the three scalars. So first sentence is let k1, k2, k3 be scalars such that k1 p1 plus k2 p2 plus k3 p3 is equal to 0 bar. What is this 0 bar? This 0 bar is the 0 vector of this p2. And what is the 0 vector of p2? 0 plus 0x plus 0x square. That is the polynomial of degree 2 with coefficients as 0. So this is the 0 bar of this P2. And substitute P1, P2 and P3, and then apply the definition of scalar multiplication and addition. We have this, that is collect the coefficient, constant coefficient in one bracket, the coefficient of x, the coefficient of x and the coefficient of x square. So is equal to 0 plus 0x plus 0x square. And after comparing LHS and RHS, we have 5k1 plus 9k3 is equal to 0. Then the coefficient of x in LHS is minus 6k2 minus 6k3 is equal to 0. And the coefficient of x square is k2 plus k3 is equal to 0. So we have the three equations and three unknowns. So we have to solve this system and we have to find the values of k1, k2, k3. So form the augmented matrix. So the coefficient of k1 is 5, k2 is 0, k3 is 9 is equal to 0. Then minus k2, coefficient of k2 is 0, k1 is 0, k2 is minus 6, k3 is minus 6 is equal to 0. Then the coefficient of k1 is 0, k2 is 1, k3 is 1, 0. And then we have to reduce this augmented matrix to echelon form. So we have to reduce this 5 to 1. So 1 by 5 R1 is the application. We have this matrix, this first row as it is, the second row and third row as it is. Then we have to reduce this 2 element to 0. Already these two elements are 0. So we have to reduce this minus 6 to 1. So 1 by 6 minus 1 by 6 R2 is the application. So we have 1, 1, 1, and this the first row and third row as it is. Then we have to reduce this element to 0. So R3 minus R2 is the application. R3 minus R2. So we have all the elements are equal to 0 in the last row. And so this is the echelon form. So we have to write the rank of A and rank of AB, both are 2. Rank of A is 2 and rank of AB is also 2. So the system is consistent. And we know that in the case of the system is homogeneous, this system is homogeneous. So in this case, the rank of A and rank of AB both are same, always same, because the homogeneous system is always consistent. Okay, and so, but what is the rank of A and rank of AB? These these two are equal to 2, and this is strictly less than number of unknowns. What do we have? That the number rank of A is equal to rank of AB is equal to 2, and is strictly less than number of unknowns, because number of unknowns are 3. And so this system has non-trivial solution. This system has infinitely many solutions. So one of the solution of this system is K1 is 0, K2 is 0, K3 is 0. But other than this solution, this system has another solutions. So in case of homogeneous system, so in case of homogeneous or non-homogeneous system, uh, the system has infinitely many solutions if the rank of A is equal to rank of AB is strictly less than number of unknowns. So in case of homogeneous system, if the rank of A is equal to rank of AB is strictly less than number of unknowns, then system has non-trivial solution. That is, then K1, K2, K3 are not all equal to 0. So if the rank of, if we have the rank of A is equal to rank of AB is equal to 3, then all these K1, K2, K3 are equal to 0. So remember these things. We have to use these things in the next theorem. That is, if the system is consistent, the homogeneous system is always consistent. But if the rank of A is equal to rank of AB is strictly less than number of unknowns, in that case, the system has non-trivial solutions. Means the system has non-zero solution. Means the values of K1, K2, K3 are the values of unknowns are not all 0. So when the K in what case the number of the scalars has non-zero values, that is, if when the all the scalars are not equal to 0, if the rank of A is equal to rank of AB is strictly less than number of unknowns. In that case, the system has non-zero solution, non-trivial solution. The homogeneous system has non-zero solutions, means the values of all constants K1, K2, K3 or unknowns are not all 0. But if the rank of A is equal to rank of AB is equal to number of unknowns, in that case, the homogeneous system has only 0 solution. That is, the values of all the unknowns K1, K2, K3, K4 are equal to 0. So remember this thing. Here we have the rank of A is 2 and rank of AB is 2, and it is strictly less than number of unknowns because number of unknowns are 3. And so this system has non-trivial solution, non-zero solution. That is, K1, K2, K3 are not all 0. So how we can find? We rewrite the equation. We have K1 plus 9 by 5 K3 is equal to 0, and K2 plus K3 is equal to 0. So there are 3 unknowns, and there are 2 equations, 2 unknowns and 3 unknowns. In this system, there are 2 equations and 3 unknowns. So assign 1 unknown. What is the difference between 3 and 2? Is 1. So assign 1 unknown. So assign K3 or K2 as T or R. Use notation R, T, S, any. So what is this T? T is any real number. So suppose K3 is T, and therefore K2 is minus T, and K1 from equation 1 is 9 by 5 T. Okay, minus 9 by 5 K3. K3 is minus T. So we have K1 is 9 by 5 T. So this T belongs to R. T is any real number, and hence these K1, K2, K3, what is your observation? K1, K2, K3 are not all 0. Because if you take T as 1, then we have K3 is 1, K2 is minus 1, and K3, K1 is 9 by 5. So these K1, K2, K3 are not all 0. So these are equal to 0 if T is equal to 0. But T is any real number. So take T as any non-zero number. Then we have K3, K1, all these K1, K2, K3 are not equal to 0. So, and therefore P1, P2, P3 are linearly dependent, So what is your last sentence? P1, P2, P3 are linearly dependent because K1, K2, K3 are not all 0. So when the system has non-zero solution, when all the unknowns are not equal to 0, if the rank of A is equal to rank of AB is strictly less than number of unknowns, and if rank of A is equal to rank of AB is equal to number of unknowns, in that case the system has zero solution, that is the values of unknowns, all unknowns are equal to zero. So I have to use this in the next theorem, this thing in the next theorem, this concept in the next theorem. So let S be the set of two or more vectors from vector space V. That is, S is the set of two or more vectors from V, that vector space V. Then prove that S is linearly dependent if and only at least one of the vector in S is expressible as a linear combination of the rest of the vectors in S. So L dot C dot means linear combination. L dot D dot means linearly dependent. So and L dot ind dot L dot ind dot means linearly independent. So these are the short form to use the linear combination, linearly dependent, linearly independent, and V dot sp dot means vector space. So what is the theorem? Let S be the set of two or more vectors from V, vector space V. Then prove that S is linearly dependent if and only at least one of the vector in S is expressible as linear combination of the rest of the vectors in S. So this is the if and only type theorem. So we have to prove this theorem in two parts. So first, let S is equal to V1, V2, Vr. Let take S as a set of more than two vectors. So obviously this R is what? Greater than or equal to 2. That is, this set S contains two or more than two vectors, V1, V2, Vr. Obviously these V1, V2, Vr are the vectors from vector space V. Be the set of vectors from vector space V. Okay. So this is one of the subset of this vector space V, contains more than two or more than two vectors. Okay. And now we have to prove the theorem in two parts. First part, assume that S is linearly dependent. We assume this S is linearly dependent. And now what we have to show? We have to prove at least one of the vector in S, that is out of this R, at least one of them is expressible as a linear combination of the rest of the vectors in S, or the remaining vectors in S. So this way, this set is linearly dependent. And then what is, by using definition, there exist scalars k1, k2, kr not all zero. That is, at least one of them is not equal to zero, such that k1 v1 plus k2 v2 plus k3 v3 plus dash 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 kr vr plus kr vr, right? Remaining statement. Then k1 v1 plus k2 v2 plus k3 v3 plus dash 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 kr vr is equal to 0. So write this complete sentence. There exists a scalars k1, k2, kr not all 0, such that k1 v1 plus k2 v2 plus k3 v3 plus dash 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 plus kr vr is equal to 0. Suppose ki is not equal to 0. I runs from 1 to r. I is what? Either less than or equal to r, greater than or equal to 1. So assume that out of this k1, k2, kr, ki is not equal to 0. The vector of ith number is not equal to the scalar ith number scalar, that is ki is not equal to 0. Not all 0 means one of them is not equal to 0. We don't know which one is not equal to 0. So I assume that ki is not equal to 0. Obviously, value of I is what? Either 1, 2 or r out of this. So value of I is what? 1, 2, r. So then we take that ki remain, that ki vi in the LHS. From this equation we remain ki vi in the LHS and shift all the remaining quantities to RHS. So what are that? Minus k1 v1 minus k2 v2 in this way, plus dash 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 the quantity minus ki minus 1 vi minus 1, that is the previous quantity of ki vi. Then the quantity after the ki vi is minus ki plus 1 vi plus 1 minus dash 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 minus kr vr. So complete this statement. First k1 v1 plus k2 v2 plus k3 v3 plus dash 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 kr vr. So remain the ki vi term in LHS and shift all the remaining terms to RHS. We have this. And then write this minus k1 v1 as minus in bracket minus k1 v1. Similarly this minus k2, write in bracket minus k2 v2, and in this way minus ki minus 1 vi minus 1. Then Similarly, plus minus ki minus plus 1 in bracket vi plus 1 dash 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 minus kr vr. So multiply by minus 1 by 1 by minus 1 by ki, because ki is not equal to 0. So multiply throughout by 1 by ki, that is divided by ki throughout. So we have vi, and this is minus k1 by ki v1 then minus k2 by ki v2 plus dash 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 minus ki minus 1 by ki vi minus 1 plus minus ki plus 1 divided by ki vi plus 1, and this way plus dash 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 minus kr divided by ki vr. Okay, so after dividing by ki we have this, and observe this minus k1 by ki minus k2 by ki, this all these up to minus kr by ki, all these are scalars, and therefore what is this expression, what is the RHS of this expression? The RHS of this expression is what? Is the linear combination of v1 v2 dash dash vi minus 1 vi plus 1 vr. That is, this is the linear combination of the vectors in S except vi. Okay, and so vi, so what do we have? Vi is equal to, this means vi expressed as a linear combination of the vectors in S except vi, or other than vi, or rest of the vectors in S. So what do we have? That is, this expression, this equation says that vi expressed as a linear combination of the rest of the vectors in S, that is other than vi. This is what is RHS, is the linear combination of vectors in S other than vi. So vi expressed as a linear combination of the rest of the or remaining vectors of vectors in S. So this is the part 1. Now so we say that one of the vector in S is expressible as a linear combination of the rest of the vectors in S. Now we have to prove the second part. We assume that one of the vector in S, say v1, is expressible as a linear combination of the rest of the vectors in S. Suppose v1, out of these v1 v2 vn vr, we assume that v1 expressed as a linear combination of the rest of the vectors. That is, what is your assumption? That is, there exist scalars k2 k3 kr such that v1 is equal to k2 v2 plus k3 v3 plus kr vr. Either write these bar at the top of v1 v2 v3 v4 vr, or without bar. So we assume that one of the vector in S, suppose v1 is expressible as a linear combination of the rest of the vectors in S. That is, there exist scalars k2 k3 kr such that v1 is equal to k2 v2 plus k3 v3 plus kr vr, means v1 is expressed as a linear combination of rest of the vectors v2 v3 vr. And then we shift this v1 to RHS, it becomes minus v1, and write minus v1 as minus 1 into v1. So the remaining vectors are plus k2 v2 plus k3 v3 plus kr vr is equal to 0. So LHS, we have, after shifting this v1 to RHS, we have is equal to 0 in LHS, and after interchanging the sides, we have this. And this is the, this, if you observe this LHS of this above this equation, so what is the LHS? Is the linear combination of v1 v2 vr, and is equal to 0. But these coefficients of v1 v2 vr are not all 0, because we are not guarantee about this k2 k3 kr are not equal to 0 or equal to 0, but this minus 1 is not equal to 0. So what is this? This equation satisfies with scalars. So this is this satisfies with the scalars minus 1 comma k2 k3 kr, and these scalars are not all 0, because this minus 1 is not equal to 0. This k2 k3 kr, suppose this k2 k3 kr all are equal to 0, but this minus 1 is not equal to 0. So all these scalars are not equal to 0. So these scalars are not all 0, and so set S is linearly dependent, because we have the scalars not all 0, but their linear combination is equal to 0, and therefore by using the definition, if all scalars are not all 0, then set is linearly dependent. So the set yes is linearly dependent, and that is we have to prove. In second part, we have to prove yes is linearly dependent, and hence the theorem, that is, if the set is S is linearly dependent, then at least one of them in S is expressible as a linear combination of the rest of the vectors in S. So its equivalence statement is what? The equivalence statement of this statement is what? The set, if S is set of two vectors or more vectors, two or more vectors in from the vector space V, then the S is linearly independent. What is its equivalent statement? S is linearly independent if and only if, at least, or there exists, its negation is for all. So S is linearly independent if and only if no vector in S is expressible as a linear combination of the rest of the vectors in S. So what is the equivalent statement of this statement? That S is linearly independent if and only if no vector in S is expressible as a linear combination of the rest of the vectors in S. So it is the equivalent statement of this statement. If when S is linearly independent, when this set S is linearly independent, if in the set S no vector is linear combination of the rest of the vectors in S. So this is the theorem. uh, then we have to define the dimension and the basis of vector space. So before that, we will see some more examples of linearly dependent and independent. So, or in the next topic, basis. So the basis topic is depend on the spanning and linearly dependent independent vectors or set. So this basis topic is the combination of the previous two topic, that is the spanning topic and the linearly dependent and independent. So this is the repetition of the topic linearly dependent, independent, and spanning, the previous two topics. So we'll see the next topic, basis and dimension of vector space, in the next lecture.